everyone, we're looking at the next part in our area of our different polygons. So far, we've just been working with one shape at a time. So now we're going to start putting some of our figures together to make what we call a composite figure. Now, there are a couple of formulas that we need to look at first for these composites that aren't considered polygons. Remember, polygons have to have straight, flat sides made up of segments. Polygons are not curved. So that means when we look at the circle, a circle is not considered to be a polygon, but we can still get how much is to the edge of the circle and how much area a circle has. So let's look at just a little bit of vocabulary about a circle here. So first thing I want to kind of talk about is when we have our circle, and this is very important for our formulas. When we have a line that goes all the way through the middle of our circle, that is called your diameter. Sometimes when they give us the diameter, we can use that value to find different pieces of information. The other thing that we are going to be looking at when it comes to circles, so let me get another circle here, are the lines that go from the center to the edge, and we call those the radius. So when we get these values, we can use them for our different formulas. So let's see what two formulas we're going to be working with. All right, so first one we're going to look at briefly is circumference. Now, circumference is basically the perimeter of a circle. But more specifically, again, because perimeter is coming from polygons, if we're looking at a circle, since it's not a polygon, we can't call it a perimeter or not. So we end up calling it circumference instead. So it is the distance around the circle's edge. Now, to get the circumference, again, we're going to be working with this, just like we worked with perimeter of our polygons. There's two formulas we can use. One of those formulas uses the diameter. So circumference can be found by taking the pi, which is 3.14159, ... the numbers keep going, times that diameter. The other option we have is 2 times pi times the radius, because in reality, it does take 2 of the radius segments in order to make a diameter. So we've got those two formulas there for circumference. Now, the other thing that we get with circles is area. How much space is inside that circle? So for our area, we need the same pi times your radius squared. So we have to use radius for area. We don't have any other option. So we're going to be using these formulas throughout parts of our composite figures. So let's look at the composites real quick. So what, first off, is a composite figure? Well, a composite figure are figures that are made up of 2 or more figures that are either combined together, or they might be 2 or more figures that are overlapping. And it is very specific over which kind of method we use. If our figures are just combined together, meaning they're just side by side, or are they overlapping? Is one covering up part of the other? Because whichever it is, that is a different method of solving. So let's look at the first method of solving, which uses addition. So when we use the addition method, this is when our shapes are combined together. Which really just means they are side by side right next to each other, like our example we have. So let's take a look. So example 1, find the total area of this composite figure. So this is made up of more than one shape. All right, yes, the whole entire outer edges here, there are 5 sides to this, but it is not a regular polygon, so I can't do an apothem. That's where the composite figure idea comes in. So we first need to identify what kind of shapes are being put together combined to make this pentagon? Well, one big shape that I first recognize is the rectangle that's on the bottom. And I have a formula to find the area of this rectangle. All right, so for the rectangle, we have to use base times height. I'm gonna make that a little bigger, a little bit easier to see here. Okay, base times height. So I need to find a 90-degree angle. I've got one down here in the corner. I have my height, which is 6. I have the base, which is 10. So let's put that in the formula. Let's get it set up here. So base times height. So 10 times 6. So this first part will give me 60. Now we're going to add to that the area of the triangle. For triangle, I need base and a height, and then I have to divide it by 2. So let's go back over and look at our shape. On top is where we have that triangle. And so we are going to now make that a little darker. We're going to find the area of that. So notice the 90 that's sitting there in the middle. So that means my base is along the bottom, and there is my height. My 3, if you notice, goes from bottom to top. So there's my height. The base we get from the rectangle. Just like we had the 10 at the bottom of the rectangle. Remember, a rectangle says opposite sides are the same. So we can copy that 10 over, and there is the base of the triangle. So we have a base of 10 times a height of 3. Divide that by 2, and that'll give us our total. So let's see what we get. We've already done 10 times 6. Now we have 10 times 3, which is 30. 30 divided by 2 means I have 15. So 75, we were in meters. So then meters squared is my total area. So now let's keep going and try the next one. Example 2. Again, try to identify the shapes. It does not matter which specific order you start in. But again, if we notice there's no overlap here, we have first shape I notice is down at the bottom. We have a rectangle. So again, a rectangle, base times height. So let's start with that. All right, now, if you notice across the top this time, that's where we have a 20. That 32 goes all the way across, and I don't need all 32 for my rectangle. That's where that 20 is going to come in, because only 20 out of that 32 goes to the rectangle. When I take away that 20, I get 12 for that other side there. We know how tall the rectangle is. That's where our 14 comes from. So right now we have base times height, 20 times 14. When I multiply those together, 280. Now let's see if we can find another shape. Next shape I notice is the triangle that's right next to it. So now I'm going to work with that triangle. I already know how tall it is because it's the same height as the rectangle, so I can copy my 14 across. I already found the base, which is my 12. So let's multiply those. Base times height, divide by 2. So 12 times 14, divide by 2 gives me 84. We've almost done all our shapes. Now we can do this top piece that kind of looks like a dome. This is actually what we call a semicircle, or half of a circle. That 20 that's sitting here, if you notice, goes all the way across. So like we said earlier, that is the diameter, but the radius is what I need for area. which would be half of that circle. I'm sorry, half of the diameter. So now we're going to do the dome. Again, our radius was a 10. So pi times 10 squared. And remember, since I have half of a circle, I'm going to have to cut that in half. So we're going to leave the pi where it is for the moment. 10 squared is 100, and all of that will be over 2. And now let's put this inside our calculator and add all of this up to get our total area. So we have 280 plus 84 plus, now comes our half a circle. So if you notice, the Desmos does have a pi button right above tangent, just to the left of the 4. We want to use that button. We do not want to use just 3.14 because we want as many digits as we could possibly get, which means we use pi. And there is my final answer, 521.07. So we need to round this off. So because of that 7, I'm going to round that 0 up to a 1 and round it to the nearest 10. So 521.1. So my area is about 521.1. We have millimeters squared. And there's my composite area for those combined shapes. Now, not always are your shapes just going to be combined, and that takes us to method 2, which is the subtraction way. So for subtraction, this is when your shapes are overlapping. And you have to make a decision when your shapes are overlapping each other, meaning part of the shape is covering another. You have to decide which shape is on top or which shape is covering part of another. You have to make that decision because it is very important. The one that is on top or covering up part of the other one is the one that must be subtracted out. So let's see what happens. So right now we do have our circle going on. And if you notice, the only parts of the circle that we can see are these little slivers underneath that shape. So we do have overlap, and the pentagon is covering up part of the circle. Since the pentagon is resting on top, it has to be minused away or subtracted away. So we need to get the pieces of our formula here. So we're going to have to take the whole circle. So what do I need for a circle? For area, I need a radius. And I do have that. There is our center of the circle. This segment goes all the way across the circle. And so that has my radius, which is the square root of 89. So let's get that part of the formula first. Area of the circle. So pi r squared. So that's going to be pi times. Now, because I'm having to put an exponent with this square root, you do really want the parentheses here. So pi times radius squared. Now we need the pentagon. So just to remind everybody what the pentagon formula says, I'm just going to move this out of the way. Our pentagon formula was the apothem times side length times number of sides over 2. So we need to go back to that pentagon and get all 3 of those numbers. All right, so your apothem is from the center of the shape to the middle of the side of the pentagon. In this case, that is my 8. So our apothem is an 8. We need the length of a side, which we do have it. It is our 10. Notice the arrows pointing to the side there. And we need to know the number of sides, which is 5 for that pentagon. So let's plug in all of this into our formula. So the apothem, which was our 8, times the side length of 10 times the number of sides, which is 5, all over 2. Now, for time, I'm not going to go back to the Desmos calculator, but we would put it in exactly how it looks there in the notes. And we would have about, because we will round it to 1 decimal, 79.6. And we were in centimeters, so centimeters squared. And that would be my final area. So I recommend you go back when you get the opportunity, type that into your calculator and verify that answer. Example 4. Again, find the area of the shaded region. So now all of the bottom part of our circle is in that shaded. And we've got all of these little slices going on that we're going to need to find the area of. So again, the trapezoid is on top. So we're going to subtract the trapezoid from the circle. All right, so we need pi r squared again, minus, now remember the trapezoid formula had 2 bases to it. So base 1 plus base 2 times height over 2. So let's plug in everything we know. Let's start with the circle. First thing I need is a radius. So we've got the center. Our 20 goes all the way across. So that means the diameter is 20. Cut that in half. My radius is 10. So pi times 10 squared minus, now we need the trapezoid. So that 20, again, all the way across, which means that 20 is one of your bases. The 12 is across the top. There's my other base. So let's say base 1 can be 20, base 2 can be 12. You have your height, which is our 8. So now let's plug that part in and see what we get. So minus, I'm going to put all of this in parentheses. We need base 1, which again we said was 20, plus base 2, which is the 12, times our height, which is 8, all over 2. And that will give us our final answer. Have a feeling we're going to round. So when we put all of this inside our Desmos, this one I will go ahead and put in just because of all the parentheses. So we had pi times 10. All right, let's try this again. Pi times 10 squared minus, all right, now we have our divide here for the trapezoid. So on the top, we had another little parentheses, 20 plus 12, close parentheses, times our height of 8, all over 2, close that final parenthesis, and there is our value, 186.15. So the 5 will make that 1 round up, 186.2. And we are in centimeters again. So centimeters squared, and there's our final. So far up to this point, we've only had 2 shapes put together, either combined or put together to have an overlap. We can have more than 2 shapes. That's why the definition of composite says 2 or more. So let's see what happens now in example 5 when we have 3 shapes going on. you actually have both happening. You have two shapes that were combined, and then a third one was overlapping part of one of your figures. So let's start with the combine first. We have a trapezoid, a big trapezoid that's here, that was combined with the semicircle, the half circle on top. So let's get that part first. We are going to have to take our trapezoid shape, add to it the semicircle, and inside the shape, if we go back for just a second, is possibly another rectangle, a 10 and a 10. So again, if your opposite sides are parallel and congruent, we would have 10 all the way around, making this in reality a square. And since that square is on top of the trapezoid, we will have to then minus it out. So let's get all our formulas real quick. So trapezoid said base 1 plus base 2 times the height over 2. I only need half the area of a circle, so pi r squared over 2. And then our square said take the side length and square it. Let's find all our numbers. All right, now the trapezoid does have a bottom length of 18. 18 does go all the way across. Now I need the top part of the trapezoid. And here's where we have to watch very, very carefully. So far, all I have, I mentioned last assignment, this dashed stuff that's here in the middle is there just as a guide to help find missing bits of pieces of information that you need for the rest of the figure. So right now, I do know I have a length of 1 here and on the right. So far, that's only 2. But this is where knowing that square is going to come in. If we notice, the top of the square is the exact same width as that missing piece we need for the trapezoid. So this piece is also 10, and that's also the diameter of that half circle. So when we come over at least to our circle, I know the radius of that. So my radius right now is a 5. I know the side length of my square was a 10. Let's finish the trapezoid. So across the top of the trapezoid, we have a 10 and 2 ones, meaning 12 all the way across. I already know how tall my trapezoid is from the 14. So now we have all the numbers we need. Let's plug it all in. All right, so let's start with the trapezoid. I'm going to put it all in parentheses because it's one shape. So base 1 can be 12, base 2 can be 18, times our height of 14 all over 2. There's our first shape plus our second shape. Now we're going to add the circle, the half circle, sorry. So pi times 5 squared over 2 minus our square. And if my side length is 10, then minus 10 squared. And we can put all of this in our calculator. So let's go ahead and do that. I'm going to use all of those parentheses. All right, so let's do the trapezoid. 12 plus 18 times the height of 14 all over 2. Close those parentheses. Plus, now we'll put in our half circle. Pi times 5 squared over 2. Close the parentheses, and now we'll take away the square, which was 10 squared. And there is my final 149.26. So that 6 is going to make the 2 round up, 149.3. So we've got a total composite area here, 149.3, and we were in feet, so feet squared. And there is my final. So again, guys, you just have to pay attention to how the shapes are being stuck together. Again, if there's overlap, if one shape is on top of the other one, the top one has to be subtracted out. But if your two shapes are just side by side, no overlap, no white space covering anything, then we just find each piece added together. So guys, please don't hesitate to reach out to me if you have any questions at all. Bye, everyone.